Hello, everyone. Welcome to the ML at GT seminar. Today, I'm very honored to introduce Ankur. Ankur is a senior research scientist at the Google New York office, and he is also an adjunct assistant professor at NYU. His research interests are about natural language processing, more from a machine learning perspective. Recently, his work has been about high precision text generation, which he is going to talk about today. Ankur received his PhD from Carnegie Mellon Machine Learning Department in 2015 and received the Best Paper Award at EMLP 2014 and also Best Papers at Translational Bioinformatics. So let's welcome Ankur and then feel free to get started.
Okay, thanks everyone for having me. So this is joint work with Thibaut, Ran, Shujia, Sebastian, Sashi, Manal, Bhuwan, D, and Dipanjan, all at Google Research. Okay, so I'm going to talk today about neural text generation. And I think a lot of papers recently, especially when you build big language models, have shown that it's surprisingly fluent, very coherent. But it's prone to hallucination, which means that the models often generate phrases that are either unsupported or contradictory to the source. And this makes them unsuitable for a lot of real-world use cases. And what we're going to talk about is that we're going to study this problem. We're going to see that the challenges come from different dimensions, not just from the modeling side, but also from data and evaluation. And so this is one of the papers that inspired this effort. This is the RotaWire dataset that was released in 2017. Here you can see that on the left, the source is a table of statistics from a basketball game, and the right is a summary of the game. And so the goal of the neural network is you ingest the source data, and you output this target summary. And what the author showed is that if you look on the right, this is a neural output, and the model outputs very coherent text. It talks about who won the game, what happened in the first quarter, who the top scorers and the top rebounders were, etc. But a lot of these statements are wrong, or they contradict the source. And this is highlighted in blue and red. So the blue is the things that are faithful to the source data, and the red is the things that are unfaithful. And you can see that the model gets wrong certain scores, who won or lost. It claims the Rockets were able to out-rebound the Rockets 49-49, and all kinds of statements like that. And this is not just restricted to this data set. This is Wikibio, where here you given a source info box from Wikipedia about a person, Frank Lino. You need to generate a one-sentence description about this person. And you can see that the model hallucinates that Frank Lino is a criminal defense attorney, which is not supported by any of the source data. We're going to be focusing a lot on data to text for this talk, but the problem is not limited to data to text. So one cause of hallucination is not necessarily the model. It's often the data. So oftentimes, because of the way we collect large-scale data sets, we basically heuristically pair different sources and targets. So for instance, when the authors constructed Wikibio, they took for the source, they took the Wikipedia info box of Frank Lino, and then for the target, for the gold reference, they took the first sentence of the Wikipedia page. And you can see that here, and you can see that there's an entire phrase about him being in the Bonanno crime family and later becoming an informant that's not at all supported by the source. And so when you train a model on this data, it's naturally encouraged to produce things that are not supported by the source data. Another issue that causes hallucination is eval. So we typically tend to try to maximize some automatic n-gram metric like BLEU. And BLEU, unfortunately, does not really favor precision. It favors coverage and fluency because of how it's constructed. And so here you can see that this table is about Michael Dahlquist. And the reference is that Michael Dahlquist was as a drummer in the Seattle band Silkworm. And candidate 1 gets the highest BLEU score, but candidate 1 is wrong. It says that he was in the California band Grateful Dead. But this happens to be kind of a similar length to the reference, and it matches a lot of n-grams, and so it gets the highest BLEU. And model selection and model development would favor this type of candidate. whereas candidate 2 is a more conservative statement, but because it's shorter, blue will give it a low score even though it's correct. And candidate 3 is not really shorter, but it's giving a different fact from the source data than the reference has, so it also gets penalized, even though it also said something. And lastly, because of noisy data and other types of phenomena that we'll see, loss functions like maximum likelihood are often not suitable for stopping hallucination. Basically, given the previous gold positions, y1 to t minus 1, you want to do your best at predicting yt, and this makes the model kind of prone to guessing and using kind of its like heuristic language model knowledge that it's learned from pre-training to hallucinate. So we've been working on this for a couple of years, kind of along 3 different dimensions: data, evaluation, and models. And then we have an orthogonal effort on unsupervised machine translation, which I won't talk about this talk. And I'm largely going to focus on kind of one paper from each category. Are there questions before we move on to the actual content?
Not at this point.
Okay. So the first thing I want to talk about is a data set that we built. That's in EMNLP this year, and you can find the data set at this link. So to present an overview, our dataset ToTTo presents a novel controlled generation task where, given a source that's a table, a set of table metadata, like the table title and the section title, and a set of highlighted cells, to output a 1-sentence target description. So in this case, we have a table about Robert Craig, who's an NFL football player, and the table describes certain statistics that he's acquired over the years. And we see that the years he played are highlighted, as well as his total number of rushing and receiving yards. And we can see the target is using information from the table metadata. We can see that some of the statements in the target are supported by the table, but not directly in it. They require some inference. So for here to conclude that Craig finished 11 seasons, you have to count from 1983 to 1993. And some of the phrases, like the rushing yards and the receptions, can be copied from the table along with the column headers. So I first want to talk about kind of what motivated us to build this dataset and why we think it could be useful to the community for helping to analyze and stop hallucination and build high precision generation systems. And so we talked about how a lot of hallucination is caused by data, where the target contains noisy information that cannot be inferred from it. And this makes it unclear often whether hallucination is caused by modeling weakness or data noise. And so what we do to separate this phenomena in our work is that we're going to have a novel annotation procedure where annotators will start with existing Wikipedia sentences that are natural but maybe noisy, and they will edit these sentences so that they're fully faithful to the source. And this results in something different than what would happen if you asked the annotator to write a sentence from scratch. If you ask an annotator to write something from scratch, they'll typically write something very boring, and which doesn't have much interesting variety or different linguistic phenomena that you will see in our dataset. The other aspect of our dataset that's worth mentioning is the task definition, which is specifically that we have a table and we have a subset of highlighted cells that are highlighted, and the model is kind of guided to talk about those. And the reason we did this is because we think this makes the task a little bit more controlled and easier to evaluate. A lot of generation tests these days are defined as summarization, and with summarization, there's a lot of subjectivity in what the correct output is. For instance, in this data set here, if you have to output a paragraph summary, there are many different facts or phrases from the table or pieces of information that might be relevant, depending on what types of things you're interested in. On the other hand, there are other data sets like WebNLG that focus on kind of just verbalizing a fully specified meaning representation, like a sort of a semantic parse or something like that. But it's often very easy for neural networks to write fluent text, so this may not be sufficiently challenging. So our data set is novel in both of these ways. In terms of task design, we have these set of highlighted cells which give guidance to what to generate. But as you saw from the example, the model still needs to infer things about the surrounding cells or from the metadata, et cetera, to produce the correct target. And in terms of annotation process, the annotators iteratively revise natural sentences on Wikipedia so that they're faithful instead of writing something from scratch or using noisy targets. And this gives us 120,000 training examples, 7,500 dev examples, and 7,500. So I'll briefly just describe how we collected the data. So we basically got a bunch of tables from Wikipedia, and as you can see, they're about different topics. And the tables have different formats and different schema. And then we use heuristics like word overlap or hyperlinks, find sentences that may be related to the table. So for instance, this table is about Gabriel Becker, and we found this heuristic sentence. After winning the German under 300 meter title, she was selected to run in the 1995 World Championship, etc. And now we can see that the sentence is related to the table, but there are many phrases that are just not supported by it, right? So the table does not talk about that she won the German under 2300 meter title. It's also not a standalone sentence. As you can see in blue, it has a pronoun, which is not desirable. Ideally, you would replace it with a proper noun to make the sentence standalone. So what the annotators do then is they perform the following task. They first highlight cells that support the sentence. So here they highlighted 1995 World Championships. They also highlighted 100 meter because that's what supports individually, and 4 times 100 meter relay because that's what supports relay in the sentence. They then delete all the phrases in the sentence that are not supported by the table. This results in things that can often be kind of ungrammatical or not a complete sentence. So then in the next stage, they perform decontextualization. So they make the sentence standalone. They replace the pronouns with proper nouns and sometimes add verbs and things like that to make the sentence make sense. And then finally, they perform a grammar correction step to, since there were a lot of edits made, we find that some of the sentences are ungrammatical and need some minor change. This gives us a training set of about 120,000 examples. We can see the vocab size is pretty large. It's 136,000 because the data set is open domain over Wikipedia. And one thing that's interesting is that you can see that the tables are reasonably well sized, right? There's about 87 cells per table as a median, which if you had to write a one-sentence description would make the task very ill-defined. But because we have these highlighted cells, there's only, in terms of median, only 3 cells that are highlighted. So that makes the task significantly more well defined. Okay, we can also measure annotator agreement at each stage. So basically, after deletion, we can see that the blue agreement between the annotators is 82.9, and then it gracefully degrades as you perform more steps, which is something that you would expect. And this is significantly higher than the blue agreement you would get if you computed the blue between the original sentence and the revised sentence, like in the 40s. We also analyze the linguistic phenomena in this data set. So on the left, you can see a topic distribution. You can see half of the topics are about sports and countries, and the other half are kind of tail topics, which we can see can be very challenging to the model. Even sports, even though it's a majority topic, it can be challenging because a lot of the interesting reasoning examples are in. We then took 100 randomly chosen examples and did some manual analysis. And so we see, for instance, that 21% required reasoning, 13% required comparisons across row, columns, and cells. Are there questions? I can look on the thing before I. No. Okay. So we ran a few baselines to kind of see how they did on our data set. So the first is a BERT-to-BERT model, which is a BERT initialized encoder-decoder. Then we run a pointer generator, which is a sequence-to-sequence LSTM model with a copy mechanism. And then there's a kind of a content planning model for data to text, which is kind of specifically designed for data to text. We have 3 metrics here. There's only 2, BLEU and parent, in the paper. And we also report BLEURT, which is a learned metric on our leaderboard. We can see they all agree in terms of the relative ranking of the systems. The BERT-to-BERT model performs the best, followed by the pointer generator, and finally the content. Then we did a human evaluation of the top performing model, and we're going to compare sort of the headroom with a human oracle. So the way we compute the human oracle is that the dev and the test have multiple references. They have 3 references. I hold out one reference and pretend it's like a model prediction. And then the human annotators are asked to compare that with the other 2 references as well as the source table. And that's where we get the oracle scores. We see that the oracle is 99.3% fluent and 93.6% faithful, which kind of makes sense with Annotator Agreement, things like that. And then the top performing model, BERT-to-BERT, is considerably less fluent. It's about 10 points less fluent, and it's about more than 15 points less faithful. And this is evidence for one of the key questions that we were interested in asking in this work, which is that even when you clean the data, do neural models still hallucinate? And we find that is the case. So even though our targets are cleaned, the models are still not completely faithful to the source. These are some examples of challenging examples in our model. So the first kind of category is rare topics. So these are things that the model hasn't really seen that much of in the training data. It really doesn't know how to interpret some of these things, these tables, when it sees it in test time. And so this table is about microdrives, and the reference is very informative. It says the second generation of microdrive was announced by IBM in 2000 with increased capacities of 512 megabytes or 1 gigabyte, which we can see from the table. There's even some nice inference there about the second generation because it's the second row, and increased capacities, which you can compare 512 with 170. The model doesn't really understand this topic, so it just says something like there were 512 microdrive models in 2000. Another interesting example of model shortcomings is that even when the model is right, it's not as informative as the reference. So for here, this is about Travis Kelce's collegiate season. And we can see that the model is saying something that's correct. It says that he finished the 2012 season with 45 receptions, 722 yards, and 8 touchdowns, which is basically just copying from the table. On the other hand, the reference has interesting inference. It says it's his last collegiate season because 2012 is the last year out of the years in the table that he played, and how he set personal career highs in receptions and receiving yards, etc. And we think that this is one of the causes of hallucination, that even when the reference is completely supported by the table, it contains language often that is not easily implied, that requires some sort of reasoning or background knowledge. And this kind of encourages models to hallucinate because the model may not understand why second was there or why increased was there, so it might just be encouraged to make up a word. So in summary, we would really like you to try out our data set. We're also welcome to feedback or suggestions, and you can email us at this address. Are there questions before I move on to the next topic?
I have one question here. So for the so when you have the data sets and then when you read the table to do the generation, how did you deal with the table format as input? Will just like a linear representation of the table lose all the structures of the input?
Yeah, so we did something very basic, which is what people do, and we just linearized the table with kind of row column separator marks and highlighted marks for the highlighted cells. It theoretically is information preserving, but the model does not learn it. We also had a simpler version where I just take the highlighted cells and I just take the row and column headers and kind of concatenate them to the cells. This is information losing, but it seemed to work better, so that's the results of it.
Okay.
Yeah, in order for the model to get 100% to really match the reference, it needs a better table.
Okay, we have two questions from audience. The first one from Kate. Apologize, but I might have missed the first few minutes of the presentation. Is the model inferring data from tables directly, or is data parsed? Also, are those clues given to the model in the form of the yellow cells? Is that what annotators determine or model use raw data and determine relevant cells? So basically, this is about the problem formulation setup.
Yes. So the annotators are performing a different task than the model is. So the annotators basically get a table, right? And they get this heuristic sentence. And then they do this highlighting, and they revise the sentence so that it's faithful to the table. But the model's task is different. So the model's task is given only the table and the set of highlighted cells to generate a sentence. And the reason we did this is because it kind of makes the task harder, I think, because the annotator is often easy. The annotator has quirks, and so it's often easy for I think the task is much harder if the model has to generate the sentence than if it just has to generate a revised sentence given the initial one. I'm not sure if this answers the question.
Great, thanks. So the next question is, the fashion of the broadcast is that there is no interaction, so we really cannot double check whether, I hope that answers the question. So the next question is, you mentioned that in the data set, the cells relevant to text is highlighted. Can you talk about how that information is encoded, the yellow part, while passing as input to the BERT model, and also how did you clean the target to help with the hallucination?
Yes, so the first question, basically we have special tags. When we linearize the table, we have special tags if the cell is highlighted. And the model, theoretically the model can learn that. That was our first representation. The other representation that works better is just in practice, because the model has trouble learning right now with the table structure. If you just take the highlighted cells with the headers localized together. But yeah, we use these tags for it to indicate which cells are highlighted.
Okay, next question.
Yes, we clean the target using the human annotation. So the human annotators basically will do this multi-step annotation. So they will basically delete phrases that are not supported by the table and things like that to produce kind of a clean data set. And we released the outputs of the intermediate stages also, so you can, if there are other kind of tasks that people want to create, yeah, they're all in the data set that we released.
Okay, we have two more questions. Do you want to take it right now or save it later, since you also have...
I can just, so I see one question about if the model is trained from scratch or you train it on top of a pre-trained language model. So it depends on the model. So I think the BERT to BERT model is initialized from BERT. So that one is trained from, that one is built on top of a pre-trained model. And I think the leaderboard, someone also submitted a T5 baseline. So that's also pre-trained. The pointer generator and the content planning model are not pre-trained. I think they use glove embeddings. They're just trained on the data. And the other question is about, I'm not sure which one the other question is.
The last question is, I'm new to this topic, but what are the real world applications of data to text generation?
I think there are many like I think we see a lot of structured data in the world, right? Whether it's tables or it is, if you look at Wikipedia, there's like Wikidata. You look at kind of, there's financial data, there's sports data. I think there's a lot of structured data, and being able to reason about it and generate is important. I think we focus on it in this data set because I think it's a good test bed for generating precise text that could also be used for other applications like text-to-text summarization, because it's easier for a human annotator to. A lot of detecting hallucination involves around you get model outputs evaluated by humans, and when you a data kind of text problem kind of makes this table kind of the world, right? The world is much smaller, right? It's not like whether this phrase is true in all of the world. It's only whether it's true according to this table, and I think that makes things easier to evaluate and to study. So I think that's why we focused on it for this data set. I think, yeah. I should move on?
Yes, thank you.
Okay. So I will next talk about eval, right? So I think key to, we can have data sets and we can have models, but if we cannot actually evaluate them and detect if they're precise, then not very helpful. So I'm going to talk about BLEURT, which is a learned metric for text generation, and Thibaut Salam in our team has led this effort. And so metrics are a very large bottleneck to generation progress. And I think that what you want from a metric is often different depending on the task. So here, for instance, this is predictions and references from the ToTTo dataset. We see that different model shortcomings have different types of characteristics depending on what we're looking for. So sometimes it's obvious that the prediction is wrong. Like in the first one, there's a lot of incorrect word overlap. And so like an entire, half of the sentence doesn't match the reference. So it's very easy for any metric to conclude it's wrong. However, in many cases, the differences are very subtle. So in the second example, the model is only wrong because the two numbers 8 and 6 are wrong, right? Whereas the correct numbers are 6 and 5. And blue would not, for instance, be able to sense this. And another interesting case is that even if model is correct, sometimes it's not as good as the reference, right? So what we're arguing is that because we have specific task-oriented relationships that we want to measure, learned metrics are very good for this, right? Because you can basically take a classifier, you can take BERT, you can fine-tune it on whatever ratings data you want that has whatever, the scores can mean kind of whatever you decide you want them to measure, and then you'll get a learned metric that behaves like a classifier. The problem is that this is brittle and it requires a lot of fine-tuning data for every new data set or task, right? So just like when you're building models or classifiers, every time you want a new one, you have to go and get a bunch of labeled data. And what we want to address is we want to try to make it robust so that we can have really fast adaptation. And so what we propose is an additional mid-training step using synthetic data to allow us to adapt very quickly to other domains and be robust to different other phenomena that you would see, like train test skew and things like that. So what we propose is that you take BERT, you first mid-train it on a lot of synthetic data, and then you have a small amount of human ratings data that you fine-tune it on to get BLEURT. And we'll show that at least when it was published, it was state-of-the-art on WMT and WebNLG. So to get the synthetic data, our goal is to generate pairs, XX prime, that resemble reference prediction pairs, right? So we want to kind of simulate model errors that we would be likely to see, for instance, deletions or word substitutions, as you can see on the right, with related words, like replacing Tuesday with Wednesday, or adding adjectives like grocery, or having repetitions like on Tuesday, on Tuesday. And these model errors are not kind of things you typically find in paraphrasing data sets. So instead, we're kind of using synthetic data to get large amounts of such data. And we have two techniques for doing this. we randomly mask tests, and then we employ BLEURT to fill the masks. So we take the sentence, we randomly mask out some tokens, and we fill in the masks with different phrases. And then we also use back translation, which is common for generating noisy paraphrases. So we can take a sentence, translate it to a different language like French, and then translate it back to English and get a paraphrase, which can sometimes be noisy. And then we have all this data, and we want some weak supervision signals. So we basically use a variety of already computed metrics for this multitask objective. So we use BLEU, Rouge, BERT score, entail, back translation probability, and lots of other scores. And so you can see our results here on WMT 17. The other results are in the paper. Basically, send BLEU is a sentence level BLEU metric. CHR, FF, BR, mover score, and BERT score are all other LEART metrics. We can see that just fine-tuning on the ratings data without doing any mid-training, just basically naively taking BERT and fine-tuning it, already gives us state-of-the-art. And then we get an additional gain to Pearson correlation by using our full approach, which involves this synthetic data mid-training. And so what we're really interested in addition to just kind of getting good results, is how robust this metric is. So let's say we skew the training set to lower ratings, and we skew the training set toward higher ratings, right? So this is simulating kind of extreme version of what could happen if you have a metric and the metric is fixed, but the models over time are improving. So the data the model was trained on is worse. It represents worse models than what the metric would see in a year or two, right? And so this is shown on the left, where we basically have a skew factor. And as the skew factor increases, it's like we're skewing the training set left to lower ratings, and the test set right. So there's more shift in the ratings distribution between train and test. And we can see that without the pre-training or without the synthetic data pre-training, the model is not very robust. So the different bars, the lightest gray is BLEURT with no skew, right? And as you get darker blue, it becomes BLEURT with higher levels of skew. And you can see that the performance degrades quite a bit in terms of Kendall tau, whereas both BLEU, which is in green, and BERT score are more robust. But when you add our synthetic data pre-training step, you can see that BLEURT is considerably more robust, right? It's more, it performs better than both BLEU and BERT score for all the skews except for the most heavily oriented skew. And I think this is just kind of the overall trade-off that you get when you use LEART metrics, right? They're more focused on performing well on the data they were trained on. We also experiment with WebNLG. So basically, we hold out. So there's two types of things you can do. You can hold out some of the systems in training and have different systems in test, but on the same data points. And the other solution, the other way to do a train test split is to split by the input. So you can have the same systems in train and test, but have different examples. And basically, we're measuring how quickly the model adapts. So if we look at, for instance, the bottom right, the 0 records, or 0 out of 224 inputs, is basically 0 shot. So that's when you take the model, whichever model it is, and just run it on the WebNLG test data. And here we can see that, so first of all, BLEU, TER, Meteor, and BERT score don't use any ratings data, right? So they're fixed all, no matter how much training data you have. BLEURT minus pre minus WMT is basically when you just take BERT and you fine tune it on WebNLG, which in this case, there is no WebNLG in the 0 shot. So this is the white bar, it does very poorly. You can also just take BLEURT with pre-training, but without the WMT data, and you can see this is the light blue. It also doesn't do that well, but it's much better, obviously, than not having the pre-training. And then BLEURT is basically the full system trained on WMT. So it's with the synthetic pre-training and with the WMT ratings data, but no WebMLG. And you can see that on zero shot, it actually does pretty well. It's getting comparable to the state of the art. And then as you move right, you'll see that you're adding more inputs. So the next bar is like 800 examples, then 1,000 examples, or then 2,600 examples. And you can see the model easily obtains state of the art. And of course, the gap between the benefit of doing pre-training or WMT reduces as you see more in-domain data. Are there questions about this section?
Yes. There is a question about your strategy 1. If you mask randomly, how do you decide when to add a verb versus noun, etc. in place of the masked word?
I think the BLEURT model determines that, right? So we're using BLEURT to fill the masks. So if we mask out, we have different strategies. Sometimes we mask out random tokens. Sometimes we mask out contiguous tokens. And then the BLEURT model uses beam search to pick the best fills of the mask. So the model is like a language. BLEURT is kind of like a language model, right? It kind of knows that it should probably put a verb or something. So it decides on its own.
Okay. Another question is, when you see split by system, what does system means? I think that this is in the evaluation part.
Yes. So basically, there are different models, right, that you would like to evaluate. So each, in this WebMLG task, different participants submitted their own system to be evaluated, right? So, for instance, here there are 9 systems. So there are 9 different participants in some sense. And so when we split on them, that means that some of the systems were only used for training and some of them were only used for eval.
Okay, I think that's all for now.
Okay, I will. Move on. Okay, thanks everyone for the questions and everything. It's very helpful to me as well. Okay, so lastly, I'm going to talk about models. How much time more do I have? It's 12:55, I think, right?
I think you have another 25 minutes.
Okay, there's plenty of time. Okay, so this is work that's led by Ran Tian in our group, and this is a modeling-based approach to reduce hallucination. And we're going to go back to this Wikibio dataset because I think there's a lot of hallucination in this dataset, so it's a very good test bed for reducing hallucination. We already pointed out that the reference is noisy, as we showed in the top. We've seen that the baseline hallucinates things like the occupation of someone, even if there's no occupation in the source. What we would really like to say, which is what our model will output, is only things that are supported by the source, which might be more conservative. So here, we'll just say that Frank Lino is born in October 1938 in Brooklyn, is an American. So our intuition is that what kinds of things should be saying and what kind of things should we not say. So templatic words like born or is don't convey any source information, and they can be generated by an unconditional language model that doesn't really know about the source data. So for these types of phrases, we don't necessarily need to be copying things from the source in order to be confident that they're not hallucinating. On the other hand, we see that content words that are faithful to the source generally require attention to the source, like the name of a person, the date, their nationality, etc. And hallucinated phrases are typically content words that are not closely associated to the source. So there are things that an unconditional language model would be unlikely to generate, but are also not in the source. So this gives us intuition as to a confidence score per token that we would like to define. We want this confidence score to be high if the token is a templatic word, which is in blue, or if it's supported by the source, which is in green. And that the confidence score should be low if it's not a templatic word and it's not supported by the source. So to model if the word is templatic, we basically use a base language model that is not conditioned on the source, which is probability of YT given the previous tokens. For determining if the word is supported by the source, we use a score AT, which is an attention score, which is basically a function of the attention distribution. So if we look on the bottom left, where we see that this is the probability of YT given the previous Y's and X, this is typically modeled with a softmax, where nu of T is the decoder output at time state T, and E of YT is the embedding for YT. And then there's a normalization softmax to get the probability. And this nu T is a sum of AT, which is the attention vector at point T, and HT, which is the LSTM state at point T. And we basically say that the attention score is high if AT has a higher norm relative to the other, relative to HT, basically, which is what's kind of happening here. When AT is high relative to HT and nu T, we see that the attention score is high. If it's low, then we know that the HT dominates, so it's kind of not as supported by the source. So it's not. We have a low attention score. And then we basically put these together. So we define the confidence score at position T to be the sum, which is like an OR function, to be AT or plus 1 minus AT times the base language model probability. So it's basically like either your attention score is high or the base language model probability. Now, the tricky thing is that the confidence score depends on learned parameters, right? So AT is a function of the LSTM parameters. This language model, this base language model, we also would like to jointly train ideally with the model. And so the question is, how do we jointly train this with the model? And then, of course, how do we use it at inference time? And so it's a bit of a chicken and egg problem, right? So if we knew the confidence score before training, what we could do is we could noisily clean references that we know will have a low confidence score, right? So we would know that academic, author, and radio host has a low confidence score, and we would just omit these when training the model. But since the confidence score depends on the model parameters, we don't know this ahead of time. So we employ some sort of variational Bayes EM-like alternating strategy, where basically we're going to subsample confidence sequences in training. So based on the current confidence score at a particular iteration, we subsample a sequence with high confidence to train on, right? So in this particular iteration, stage and film were not sampled because maybe they have low confidence score. And then we get a target to train on. This helps us improve our confidence score because we improve the model parameters. And then we go back and we keep resampling. We also have a nice trick in test time based on this work from Braverman et al., where we can use the confidence score to calibrate output probabilities and weigh things higher that have higher confidence score. So here, this SG means stop gradient. So this is a one-parameter model. Basically, everything has a stop gradient on it. Nothing is being tweaked except for this kappa parameter, which is kind of weighting the confidence score with the rest of the, how much to adjust the probability by the confidence score. And we can see that when kappa is 0, it doesn't do anything. But typically the model will learn a non-zero value of kappa. So our paper has some experimental results on WikiBio and WebNLG. I'm just gonna present the WikiBio ones. And then what we can do is our strategy works with many different models. So we take a pointer generator model with and without our confident decoding strategy. And we also take a BLEURT to LSTM model with and without our confidence strategy. And our evaluation metrics, as before, are BLUE, parent, and human eval. I think I'll mostly focus on human eval and BLUE, and the parent results are in the paper. So On the left here, we see is a human eval of the faithfulness, which is like the precision, and on the right is the blue. So what we see is that first, the confidence decoding significantly reduces the hallucination. So the pointer generator is 80.3% faithful, and when you add the confidence decoding to it, it gets 86.8% faithful. And similarly for the BLEURT LSTM, it's a little bit less faithful to begin with, but you also get a 4-point boost when you add the confidence decoding to it. We see that this does track a reduction in blue, because blue typically is not really, blue likes the prediction and the reference to be the same length, for instance. And typically this confidence decoding with higher confidence will produce shorter sentences. So blue is unhappy about this. We also look at fluency. We see that fluency is mostly similar to all the methods. On the right, we measure coverage by the percentage of cells, like pieces of table information that were covered. We see there's a minor drop in fluency for some of the confident models, like 39.4 to 37.8, or 38.4 to 38.7. No, I guess that one is not a reduction. That one is about the same. We can also further increase the coverage by basically using the length penalty in joint with the confidence decoding. And this will increase the coverage to be higher, but it does often come at a cost to fluency. So there's kind of trade-offs whether you want faithfulness coverage or fluency. So this is the general works that I had. We presented this multifaceted approach to tackling hallucination from these 3 perspectives: data, evaluation, and models. And you can see some links here to our data set and to the BLEURT metric, which we hope you'll find helpful. And thanks, and feel free to ask here if you have questions or to email offline as well.
Thank you, Ankur, for the great talk. So we have several questions. So I'm going to read them from the most recent one. Okay. So the first one is, how do you measure the fluency automatically in your last work?
This is done with humans. So basically, the fluency, the coverage, and the faithfulness were all human evaluated. We showed a human annotator the info box, the reference, and the candidate prediction. And we asked the human annotator to say if the candidate prediction was fluent or not. And same with coverage and with faithfulness. Okay. I agree that you could, use fluency data somewhere, and you could, fine tune a BLEURT metric to be, specific to fluency if you wanted something automatic.
Next question. I think you will like this question a lot. Have you also tried using negative example training? Basically, it's a model hallucinates. You provide it with feedback saying this phrase is not supported.
Yes, so I do really like this question. This is something that I'm very interested in. I agree that we would like to do this. And there is some work on doing this. If you look at something like unlikelihood training, they try to do this. I think it's just there's not in classification, there's a clear kind of positive and negative paradigm, right? But in generation, that's not by tradition the case, right? You kind of have, each example is like a positive, right? And you're assuming everything else in the space to be negative. And so I think there is some interesting research that we're pursuing and other people are pursuing to kind of determine what are the optimal ways of giving feedback. Because if you give, I think it's tricky, right? Like if you just give feedback on certain phrases, like in this case, it can just truncate and remove the phrase, right? But sometimes the phrase is in the middle of the sentence and it might affect the fluency of the model, for instance. And so I think it's a little bit trickier than it is for the classification case. But I think it's, I like this research area very much.
Okay, next question. How do you select the set of pre-training signals? Do different choices affect the performance of BLEURT? For example, if you use more or less source of signals. So this is regarding the BLEURT.
Yes. We have an ablation in the paper. I think the strongest one is BERT score. And then I think blue and rouge are the weakest. And then maybe the entailment and the back translation probability are in the middle. Yeah, so it definitely obviously matters what you use to, what you use to pre-train it. Yeah, and stronger signals, stronger and more diverse signals obviously help. And weaker signals, like blue is a pretty weak, it's trivial for the model to learn to imitate blue, so not as helpful.
Okay, thank you. So another question regarding the dataset work. What was your biggest challenge when building the model or preparing data?
I mean, definitely preparing the data, right? Because I think that was the main contribution of the paper. From models wise, we just kind of took things off the shelf, as I think is kind of conventional for a dataset paper. Now, I think in the future, we want to innovate more on the model side to develop better models that do more reasoning and don't have hallucination and things like that. But that paper was, like the main contribution is the new data set. So the baselines are just things we took off the shelf.
Okay, I think that's all the questions we have. So if anyone is interested, you can also contact Ankur by sending emails if that's okay with Ankur. Okay, and then last question. Steve asked, I'm curious about the BLEURT encoder and then LSTM decoder. My understanding of the reason for LSTM is for the process of text generation. However, if in order to compare the difference between the input and the output for confidence, would it be okay to use BLEURT in decoder, then compare the two attention vectors?
Yeah, so Ran and me, we had like basically the decoder right now, because of the exact formulation of the attention score, right? There's this. Let me go to the slide. Right now, it's formulated with this. It's kind of the ratio, right, of this attention score with the LSTM state, right? And I think that kind of makes sense when you have an LSTM decoder because there's these kind of two components. But BLEURT or like a transformer decoder is all attention everywhere, right? So I think the our notion of kind of attention score becomes a little bit more confusing, which is why we don't have experiments with a transformer decoder.
Okay, I think that's all the questions we have today. Thank you very much for your great talk. I think, as you can see from the questions, students really like the work that you are doing, and we want to thank you again for giving this great talk. I think that's all for today.
Okay, thanks everyone for having me and for listening.
Okay, great. So further questions, feel free to email Ankur, and then that's all for today. Thank you. Have a great day.